Good morning to everyone. Welcome to the invited talk by Professor Lena Halounova with topic remote sensing, land use, land cover data, and example of their harmonization. We will start with a short welcome note by Professor Fedon Kyriakidis, and then we will proceed to the talk. The talk is already being recorded, so please turn off your cameras and microphones. And we will allow questions only through the chat, and they will be answered after the talk. At this point, I would like to invite the research coordinator of the ERATOSTHENES Centre of Excellence, Professor Fedon Kyriakidis, for a welcome note.
Greetings to everybody. Good morning to all. I hope you can hear me. It is with great pleasure that we welcome Professor Lena Halounova, from the Faculty of Civil Engineering at the Czech University in Prague. Just a brief, short introduction. Lena graduated from the Czech Technical University in Prague at the Faculty of Civil Engineering, and basically she was doing her Ph.D. at the Department of Hydrotechnics, and then moved to the remote sensing laboratory of the Department of Mapping and Cartography, which she actually is heading today. Her research interests span a variety of topics, but she's focusing mostly on optical, SAR, remote sensing data, and GIS applications towards the solution of problems of water engineering, erosion, reclamations, landslides, land subsidence, detection of vegetation in urban areas, and change detection in urban areas. She has published extensively and has given invited talks and lectures throughout Prague and other universities abroad. She is actually currently the Secretary General of the International Society for Photogrammetry and Remote Sensing, the ISPRS, which is a very important post. And she is very dear to the EXCELSIOR project and the ERATOSTHENES Research Center, because he has been following and helping and being instrumental in promoting the mission of ERATOSTHENES and EXCELSIOR throughout both phases of the teaming project, the teaming phase 1 and teaming phase 2, which led to the funding of the project. And she is currently on the advisory board of the ERATOSTHENES Centre of Excellence, and she's providing her valuable expertise and wisdom towards the shaping the vision and the mission of the center. And we thank her very much for this talk of today. That's all from me.
Sorry, I was muted. Thank you. We will now proceed with the talk. So Professor Halounova, you may start sharing your screen.
Good morning, everybody. Thank you for introducing me, sir, and thank you very much for inviting me to give a talk, which is now related to the ongoing research we have been doing together with other colleagues. So I will start with the opening part of our project, which is focused on land use and land cover. What in fact land cover and land use means. If we look at the definition of European Environmental Agency, land use corresponds to the socio-economic description. So it means that we have in mind what is the land use for. And there is another part of a definition which is used by Food and Agriculture Organization, and I would like just highlight the part which says that grassland is a cover term, and rangeland or tennis court, these are the land use terms. So this is quite easy how to distinguish that, and land cover definition by Food and Agriculture Organization is the observed biophysical surface of the Earth surface, and it can be confined with the description of vegetation and man-made features. So, and there is also or was a discussion whether water surfaces belong to or not, but in practice, water surfaces were included as well. So continuing with the lecture, I would say that and confirm that land use and land cover are linked together, and the problem for us is and was that they are linked and combined together when we are working with data. And the combination of land use with land cover is a problem for combining the data, especially remote sensing data, because remote sensing data offers us only the information about land cover. So how to separate them, and do we separate them in the PROC data? And if we want to, we have to adapt the nomenclatures, but existing nomenclatures mostly didn't respect the separation. So to be able to decide, we have to have a look at the existing land use, land cover data. And that was the first part of our research, which we started. Oh, sorry. I cannot move. Within the project, its name is Gecharmonizer, and its a longer name is European Wide Automated Mapping System for Harmonization of Open Data based on phosphology and machine learning. So the project itself uses only open data and only open software, and the working organizations are coming from our university, so Czech Technical University in Prague, from a Dutch company, Open GeoHub, from a German company, Mundialis, a Romanian one from called TerraSigna, and Multivan from Croatia. As far as the overall objective is to provide a portal which will comprise not only the data, but also the software. And the method using for creation the data of the portal are based on machine learning, and the area which has been processing is entire Europe. So as I already mentioned, we are working with open data, and the result will be open data. One part of the project is focused on European land cover from satellite data, and the main period which we have been processing starts in 2000, and the last year should be 2020. So the result will cover the European land cover for 20 years using remote sensing data and other input data I'm going to talk about. And as far as starting with the project, we had to make a research about existing land cover data evaluated from various sources. And we analyzed their spatial coverage, thematic resolution, spatial resolution, and temporal coverage. This is an example of two outcomes. One is a product of NASA, and one is a product of CORINE. And they are examples of two different coverages. And therefore, we decided to divide these land cover data, available land cover data, to global, continental, national, and regional. As far as the global coverage, these are produced by different organizations. So the first one is made by ESA, CCI Land Cover Globe Land 30 is a product from China, from National Geomatics Center. GLC share is made by FAO, Food Agriculture Organization. GLC was created by Joint Research Center, NASA, and Japanese, and VTOL, European Organization in Belgium. There is an overview of characteristics I would like to talk about and which make the products to be different one from each other. So thematic resolution is one of analyzed characteristic, and there is quite a big difference. We have two products with 23 classes, and we have one product with 10 classes. So how to compare it? And there is a different nomenclature. One which is used by FAO, LCCS, which we can find in 4 products, and Globeland 30, for example, the Chinese with 10 classes uses its own system, and the NASA has its own system. And another completely different characteristic is spatial resolution. So it varies from kilometers resolution to 30 meters resolution. So to compare it, we made some comparison of these characteristics with the overall accuracy, which all maintainers present at their websites. So the best production is from the Globeland 30, so it was made in China. And if we, sorry, I have problem with moving. If we look at the graph, it shows us dependency of overall accuracy and spatial resolution. So global land cover 30 has a 30-meter resolution data, and it produces the data with the highest accuracy. So the tendency presents that the worse spatial resolution shows a worse overall accuracy, which is quite an important information. This image shows us that the temporal coverage plays also a quite important role. So there are data which are or were available every year, like ESA data, and some data are available only in few temporal coverage. So it's also for us an important information when we are looking for back to receive data which are related to the very year. We have to choose, in fact, from which source we can start with. Going back to the differentiation between several types, I'm going to speak about European, so about continental data. There are several of them. The best known, I think, especially in Europe, is CORINE land cover, produced by European Environmental Agency, now under the project Copernicus. The second one is European Settlement Map and Urban Atlas, again of the same organization. Land Cover Map of Europe 2017 as a product of Copernicus as well. Pan-European Land Cover 30 meters of 2015 as a work produced by Humboldt University colleagues under the heading of Pluchmacher, and high resolution layers also maintained by Copernicus. The similar table shows us again differences between individual products, and thematic resolution has a wider variation between individual types, data products. CORINE produces the data in the 3 layers with 44 different classes. On the other side, European Settlement produced the data only in one layer. So it's just an overview of urban areas of the settlements. And the nomenclature is quite harmonized. It's based on CORINE classes, even though in different thematic resolution, since we can see that CORINE product has the 44 classes and pan-European land cover, for example, 12, or S2 GLC, so Sentinel-2 used for global land cover made by ESA, 13. As far as the spatial resolution, there are also differences, but not so significant like in the global land cover. There is another graph which shows the accuracy, overall accuracy, again presented by authors. The general accuracy has raised and reaches now even 96% for the product which is produced in one thematic layer, so European settlement map. Using a similar comparison of thematic resolution and overall accuracy, we can see that there is also a similar tendency showing that the higher thematic resolution provides a worse overall accuracy. So it's a similar result as from global land cover data. As far as spatial resolution, it has the same tendency. So the worse spatial resolution produces worse overall accuracy. So if we compare these types or these pieces of information, they have similar results of characteristics. And again, there is an image showing the coverage in the temporal scale. So they are not so frequent, the data, they are more detailed, and also sometimes the time differences are not the same, like the example of CORINE data, unlike Urban Atlas, which has been produced in the same time difference and high resolution layers as well. And the third and the last group of land cover data are a list of data which were produced in individual countries. This is not a long list, so we can see that not all countries created their own separate land cover data for their country. And as an example, and all the data are publicly available, we have a product of Austria, these are the land cover of Germany, of Spain, of the Netherlands, of France, of Greece, and Hungary. There is a map showing which part of Europe, in fact, is covered by these individual national land cover data. And the table shows, as in cases before, differences in thematic resolution, which has even wider range than we saw in European data types. And we can see that the lowest number is in the product of Germany, and the highest one is in the global land cover, which was created by Hungary. This is an extremely higher number of classes. And the second highest detail of land cover layers, land cover classes, is produced by the Netherlands. As far as the nomenclature, the authors did not use always the same as those who were in the previous one. So CORINE nomenclature can be found the most frequently, but Spain has its own nomenclature also, so France its own, and the Netherlands and UK in the last column as well. I would like to show you again the overall accuracy, which as the highest overall accuracy is in fact similar or the same as the best of the European one, and the lowest one is 80%. So the accuracy is different between 15%, I would say, between 95 and 80%. And again, the two graphs and the last image, the overall accuracy has the same tendency as the previous two groups. So the higher thematic resolution results in the worse overall accuracy. As far as the spatial resolution, again, the same tendency. So the better spatial resolution produces the better overall accuracy. As far as the the temporal coverage, there are big differences as well. So the longest history can be found in the Netherlands with the highest number of individual time layers. There is a special attitude or approach to the land cover producing, and this is what we can find in UK. And Lisa is active, so the Austria country is active during the last years. So all the producers have different approach, have probably different finance sources and different projects for producing that. Just to summarize, the most important thing for us for the project, all three different groups of land cover types, data types, show that the thematic resolution, the higher one, produces worse accuracy. Why and what makes the difference for good and bad results for the land cover classification? We are talking about input data, and input data in all cases are those who are called remote sensing data. And how to choose the good one means that we need to have good quality data, and they need to represent spectral information in the way we need it. So we need such spectral resolution to be able to distinguish individual classes we are looking for. And spatial resolution of data has the influence again to the spatial resolution and accuracy of the data. A necessary temporal resolution offers us if the data are really related to the period we are processing the data for. Another big step, or another big important issue, which is related with good or bad results, is a method. And the method not only for the processing, but for collection of sample data or training data. And the last one is software. So all three issues which are here highlighted, if they are good, they produce or allow us to produce good results. And if not, at least one of them, it may cause us problems and it deteriorates the accuracy. Talking about the model which we are using of in the project, has the model three different type of data. And the first one are land cover data. So that's why I spoke about that. And I will mention which sources we have been using. And this is a list of them: CORINE data, OpenStreetMap, and LUCAS. And I will speak in a detail later on. Satellite data. I stress that the project is focused on open data, and therefore there are only Landsat, Sentinel-2, and VIIRS data from or showing us nightlight data, and other data, again, open available data, digital terrain model, monthly geometric temperature, and global surface water. So, free land cover data. Talking about free land cover data, which we used for the project, are CORINE data. So it was one source of data. And if we go into detail, we can see that it cannot be the only source. It has its limits, and I will mention why there are limits for us when we are creating the long list of individual annual years. So the first land cover was created by Copernicus project under the present umbrella of the project, CORINE land cover in 1990 already. And the preparation work started already in mid of 80s. So it has really a long history. And the Landsat and data input which were used were multispectral scanner from Landsat and thematic mapper. Participating countries were at that time 27, and the number raised up to 39, which participated in the CORINE land cover in 2018. So as you saw at the image before, there are 5 layers of the data, and the latest one is from 2018. Speaking about CORINE classes, I mentioned already that there are 44 classes. They are ranked into 3 different hierarchy levels. So the first hierarchy level is urban surface, is artificial surface, agriculture surface. And you can see that each of them has several classes or open fabric, industrial, and so on in artificial surfaces. And each layer of the second level, with one exception, is again subdivided into the most detailed classes. So the number of these most detailed classes creates the total number of 44 classes. And they are ellipses. And the ellipses are examples of what I said before, that nomenclatures are mostly a combination of land cover and land use. So industrial or commercial units in the industrial, commercial, and transport units are examples of land use. The same like port areas. And this is what makes a problem with the CORINE data as one example of problem sources. There are another 3 main classes in CORINE, and this is forest and semi-natural areas, and wetlands and water bodies. It creates all list of all classes of CORINE data, and I have here burned areas. This is one of the most difficult classes for land cover classification, because burned classes are able to be classified just for a short period, and the differences between CORINE land cover layers is longer than the detection period of burned areas. We are now working on an extra part of the project just to find a way how long we are able, or we can find, detect and determine burnt areas for a CORINE project. This is the list of some quite difficult classes in CORINE, which are again difficult related to the data source. What is discontinuous urban fabric? How can we define that? There is a publication which in detail defines the authors, the interpreters who prepare CORINE data for evaluation. So the description can be found, photographs and so on. But if we use the remote sensing data, and if you want to make the automatic classification, it's a big task. And the description is one thing and the classification is another one. But CORINE, as it was created from the very beginning, it's a visual interpretation. And our trial is to produce data automatically from remote sensing. Then there is another group of 3 classes and another of 2 classes, which can be distinguished in a problem, and another group of 3 classes. And the last 3 are again a part of a special research we are focused on now. So there is an example of the first class, which I said before, that the determination from remote sensing is difficult. If you look at how the combination of vegetation and artificial surface is different in European different countries, and a combination within related to remote sensing data resolution we are able to use, so Sentinel and Landsat. So this is mostly a problem of classification of vegetation combined with artificial areas. So to correctly detect these areas is a real challenge for the project, and not to challenge of the method, but challenge due to the data. There is example how the work with CORINE is based on individual interpretation, and how difficult for us is to use the CORINE data, how to define exactly the training data from the interpreted CORINE data. The smallest area which is mapped in CORINE data is 25 hectares. And if you find the area on the left side, which is in fact a combination of artificial surface and vegetation one, if the vegetation one is smaller than 25 hectares, it means that it disappears from the CORINE layer. But for us, the area of 1 pixel is far smaller than the area of 2 for 2. And if we use the pixel directly from the place where the vegetation area was removed from the interpretation, then we are using wrong training data. There is another example of problem of CORINE data, and you can again see the problem with the smallest area, mapped area in CORINE. So if we have 3 small areas of the same class within a distance which is shorter than 300 meters, they are combined together, and therefore the areas between the real existing class 112 are again represented with representatives of other land cover class. And this is a problem if we would like to use only CORINE data. So therefore, we tried to use another data source completely independent, whose source and creators are completely different. These are people who are not, most of them, experienced really with mapping and so on. They are just watching around and mapping according to rules which are set up by OpenStreetMap system. And therefore, if you open the main website of the OSM, you can read that the aim is to produce maps which can be relied upon. And disclaimer says the maps might not be reliable. And this is something which we again have to take into account, that we cannot rely on all the data which are available in OpenStreetMap. I do not want to criticize anybody. This is a wonderful product. When millions of people in the whole world work together, try to learn how to work with maps, but the problem is for us that we do not have 100% of the result we can find. This is one problem. And the other one is a very long and large scale in the thematic resolution of the data. There is just a starting list, which you can find on the website of OpenStreetMap. And the list shows that there are two big groups, primary features and the secondary called additional properties. And the primary features are divided again hierarchically into lower level features and in fact 2 layers. And if you open the second layer with 3 numbers ahead, you will find again individual values, which mean individual classes. So there is an example of the first 1-1 hierarchical level, area way, and the value in fact is a class as we use our definition. So there is a description, there is a map rendering, there is a photo and so on. So if you try to find out all the classes which are included into the OpenStreetMap, it's so wide that you are not able to use the data as a whole for the land cover we are aiming at. There is another example at the 3rd level. So you can see that also the 3rd level can contain individual classes. So the system is really very, very complex. If we compare CORINE versus OpenStreetMap, CORINE layers are polygons. We cannot find their line classes. And if so, they are mapped like polygons, and we can find there only highways. And the rest are only polygons. Unlike OpenStreetMap, where we can find nodes, ways, relations, and area boundaries. So this is really a rich source of data. CORINE are divided into 3 categories, and OpenStreetMap has 29 primary features, which I showed you, and the levels are 2, as I showed as well. If you would like to find more pieces of information, the methodology of CORINE was published by Kostra and by her colleagues from Hungary, who were very active from the very beginning in creating the CORINE product, and OpenStreetMap is described at the website I'm mentioning here. How we started to analyze the relation between OpenStreetMap and CORINE. So our colleagues, they've used only land use data, so they selected that, and only for the Czech Republic, and compared that with the 2nd level of CORINE. And you can see how they, in a binary way, distinguished individual relations between these classes or these nomenclatures. I wasn't satisfied fully with 2 previous types, and that's why we went and use another data sources, which are publicly available, and which is also, again, a European product managed by Eurostat. And this is not exactly land cover, but it can help land cover because these are point data, and point data in a 2 by 2 kilometers system. The years of coverage are 2005, 9, 12, 15, and 18. And it has a development. As previous systems, all these systems have its development. So they started with 270,000 points, and the year 2018 comprises already more than 1 million points, where a detailed interpretation on site combined with photo interpretation in a lower number of areas was used. There is a list of land classes used for LUCAS, and I would like to stress that LUCAS system is the only one from all these three which strictly divides land cover and land use, and shows also links between land cover and land use, which is very helpful for our project. So there is also, again, hierarchy of individual classes, the main one, artificial, cropland, woodland, and etc. Example that the land cover coverages in LUCAS are again divided into 3 layers. And there is an example which is in red color highlight and greenhouses. It's a special land cover, which in this case, it belongs to artificial land. And if you look at to land use, it has a relation to 2 completely different land use classes. LUCAS land use categories are divided into 4 sectors, into primary, secondary, tertiary sector, and other use. So it's completely different approach how to define the land use. And this is an example how the links are used for the LUCAS data. So on the left side, you can see land cover and the class rocks and stones and their relation. So the class F10 is related to U140 and so on and so on. Each class has its own definition, again, in the detailed document which was produced together with LUCAS data and which is updated always with a new layer produced by Eurostat, and showing not only the new things, but presenting relations between the previous version and new one. So there are improvements also in the production of the data. As far as the data collection, there is an example, all the point or each point which was analyzed in data in situ is combined also with photographs showing the point. Our point is now as a yellow element on the center of the photo. And 4 other photos are photos in 4 directions to the north, east, south, and west from the point of the measurement. So it allows later on to verify and to realize how the area around the point has been looking at the moment of the detection on site. There are 2 areas which define what is the land cover and land use of the point. The smallest one is created by a circle of 1.5 meter radius. And there is another one whose radius is 20 meters. So LUCAS data collection depends on what is homogeneous and what is not homogeneous as an area around the point. This is an example of non-homogeneous area where are trees combined of a grassland with grassland. So this is why the radius was enlarged to 20 meters from previous 1.5 meter. This is a photo showing, or two photos in fact, showing why in some places the radius for determination of LUCAS class was 1.5 meter radius, and why the radius on the right photograph was 20 meters, to include the information on the right side that there are surrounding trees within the area. We try to, again, to convert data between LUCAS and CORINE. So you can see a part of LUCAS second level classes and their codes, and respective CORINE second level classes, respective third level CORINE classes. And there are some question marks. So we still do not have an exact answer for these question marks. We are still working on classification. So it will be the result of classification which will help us to answer these question marks. This is a comparison of the situation of existing LUCAS table and the two systems we are now testing for the project. And the first one is in fact conversion between LUCAS 10 classes, OpenStreetMap 10 classes to LUCAS, and OpenStreetMap 20 classes to LUCAS. And it seems that probably the OpenStreetMap with 20 classes will bring the best results. But we are still, I would like to confirm, still in the phase of the research. As far as remote sensing data, as I mentioned, we are obliged to use in the project, and that's why probably was one reason why it was approved, open data. Covering the period from 2000 and 2019, we have to use data which are available for the whole period, and these are Landsat data, starting from Landsat 5 and using thematic mapper, Landsat 7, advanced enhanced thematic mapper plans, and Landsat 8 with only sensor. And last 4 years, where we still have only 2018 and 2019 Sentinel-2, but it will be enlarged for the period 2015 to 2019 Sentinel-2 data. The data for the processing are divided into 4 seasons: winter, spring, summer, and fall. And there are dates: what is winter, what is spring, what is summer, and what is fall. This slide can show you the whole workflow which has been using for the evaluation, starting from the data, sample data for the classification, pre-processing of remote sensing data, creation of the feature space and mathematical classification processing, and the final result. If we look at the individual parts of the workflow, so as I said, Landsat data were used, and I'm using here 2 words, Landsat composites. Why Landsat composites? Landsat offers each 16 days a scene from the very place. there are many areas where they did one orbit measurement, which are covered by clouds, which are covered by their shadows, and which are covered by snow in winter. So composites are a product which is a result of processing, of replacing gaps, those places where we have no information about the land cover. Sentinel composites, this is the same problem. Again, clouds, again, shadows, again, snow. And nightlight are data which are measured in infrared bandwidth, and they are combined with land cover data, so highlighting the urban areas. This is an example why we have to, in many places, not only due to shadows, but and clouds and snow, fill in the data. So the result is clear, the image shows that, and the method is based on the analysis which was presented last year. And if I'm not wrong, it was in January last year by a paper whose main author is Peter Potapov, and it was published in Remote Sensing. You can find here DOI of the paper. How to fill the gaps caused by any reason. The method which was created is called temporal moving window median, because median is used for the processing quite in all steps. And the production required to generate more than 23 million individual files, and 7 bands for sentinel data were used, so blue, green, red, near infrared, to shortwave, infrared, and thermal band. And the period was those 20 years. You can see how the final result looks like, how the gaps were filled, and I will explain you the system, how the filling was processed. In fact, there are 9 priorities which were used for gap filling. Number 1 is the best, number 9 is the worst. The first up to the 3rd priority used for gap filling the same reason. This is the best thing what we can do, to use the same reason. But there were data where the only season wasn't enough, so there were still gaps. So then it was decided to use fall and spring data, so to combine 2 seasons. And this combination creates the 4th and 6th priorities. And the last 3 priorities are based on combination of data from all 3 seasons, spring, summer, and fall. You can see that the median value appears in all cases. So combination of 1 season is always made from median values. Combination of 3 seasons as well. If we use combination of 2 seasons, there are average of medians. And what are the differences between the 1st and 3rd priority, 4th and 6th, 7th and 9th? And it is a size of moving window. And the moving window sizes are either 8 or 16 or 24. It means that we use 4 measurements before and 4 measurements after the day the pixel has no value. So this is the principle, how the gaps were filled in. And I would like to add that if none of these priorities were not able to provide the data, the producers, our colleagues which work with, they used also data from previous years. The GLIDE method, which I mentioned, which was published last year, used for evaluation of the global data from 3 years even. As I mentioned, there were remote sensing data, and not only the bands which were presented at the previous slide, but also spectral indices. And there is a list of spectral indices. I think the probably quite known for most of you who are riparian ecosystem index. The others are quite well known. And DVI, I even didn't mention the name there because it's so well known index that it's not necessary to name that. Other data which were put into the total model are timeless data. So digital terrain model, elevation of the model, slope of the model, and then 2 evaluated data types, global surface water, which shows frequency of occurrence of water if individual areas of Europe. And the frequency, in fact, is defined how many times the water covered the area. So permanent water surfaces have 100% of occurrence, and then there are areas which were never covered by water surface, so their value is 0. And as far as the monthly geometric temperature, it's a method which was developed in the paper whose detail I have on my slide at the bottom. Altogether, the data which were used for classification. This is the overview of them. So the primary data which were used are LUCAS points, and LUCAS points were verified by Copernicus and also by OpenStreetMap. Since this OpenStreetMap is in fact a vector map, we had to rasterize the maps to the scale of, at first, 10 by 10 meters, and then it was resampled to 30 by 30 meters. For the classification and validation of the result, the training data from LUCAS created 80% of LUCAS data, CORINE 80%, so altogether 80% of data. For the validation, 20% of LUCAS, 100% of CORINE. If CORINE was used, then 20% of CORINE was very used for validation and 100% for LUCAS. So altogether, the validation data were 20%. So from whole content of data which are available, we used 7 million pixels, while 5,000,003 were used for classification. Since the validation showed us the accuracy, which was around 60%, there were another approach how to improve the selection of training samples. Training data are one of base condition to reach high accuracy. So there is just a short example, not covering the whole data table, which shows how individual classes were specified in a detail. So for example, mineral extraction size had to have another conditions, that there are no trees above and there is no grassland. So this is a system which was another step to improve the classification quality. As far as the methodology, machine learning, as it was highlighted already in the project proposal, is a method used for that. And we are in the phase when hyperparameter are in the phase of tuning, when importance of individual variables are analyzed, and the method which I used is random forest and XGBoost, and deep learning method, artificial neural network. And the final result is not only classification, but also probability of the results. And small examples on the right side show how the result can look like. So the right small image of Europe is a map of probability. So as I mentioned, the 5 to 3 million pixels were used for the classification in this first phase. The classification nomenclature was based on CORINE data, however, such called in our group reduced nomenclature of CORINE data. And you can see there are a couple of classes which were not used for the classification due to the definition of classes like discontinuous urban fabric, mixed forest makes also a big problem, peat bogs, and so on. If somebody is interested how much time it took, so the area of Europe was divided, and there's 7,042 tiles into groups of 1,760 or 765 tiles, and total number was for more than 4 days, 4.2 days, to calculate one classification for the whole Europe area. To conclude, land cover, its classification and harmonization is a complex problem. So in fact, we are divided into 2 groups. One is mainly focused on technology of classification, and one is mainly focused on harmonization of a land cover nomenclatures. And the problem of the nomenclature, as I mentioned, is that mostly, except for land cover defined by LUCAS, is a combination of land use and land cover. And therefore, if there is a land use class, the land use class does not respect the spectral feature space. And this is the most difficult problem. And the other one is that due to that, individual class, which is a land use class, comprises more classes of other, and also the definition starting from individual systems do not have the relation one-to-one. Atmospheric conditions are another problem, not only due to calculate the values, but due to that we are not using the same values of different places of the same moment. So places where we are using gap-filled data have different spectral characteristics to the same area in the same region, just moved a little bit. And therefore, the classification has a more difficult role in this case. Spectral characteristics differ for the same area because of the measurement and calculation. So to conclude, as a final slide, I would like to say that the project is based on open data, is produced as an open data. Codes, scripts will be available on the website, and this open strategy created us also limits, and these were limits as far as the remote sensing data availability. So we are strictly forced to use Landsat, and nowadays in the last few years Landsat and Sentinel. And the last part of the project will be focused on improving and tuning the nomenclature harmonization, and final recommendation which nomenclature to use to produce repeatedly a reliable land cover on the whole Europe. And on the other side, the technological part of the rest of the project is focused on training the models to improve the accuracy only from the technological side of the project. So the project itself ends in June 2022, and we are still time to improve our results. Present results are already available. You can compare, you can see the differences between individual years and so on. Don't be surprised that the results are not accurate as you would like to, but still this is an example how the final production will look like. Thank you very much for your attention, and I hope there will be any questions, some questions.
Thank you, Professor Halounova, for this insightful presentation and talk. So we're waiting for your questions in the chat.
Eleni, are we allowed to only ask questions through the chat or also verbally? I guess through the chat,
I mean, if you have a question.
No, if other people do not, if they do not ask anything, I will ask at the end.
So that we can coordinate better, but
Okay.
If you want to ask something, feel free.
So I can see 9 questions. Will it be possible to receiving a record of the lesson, please? This is not a question to me.
Yeah, I already replied to this.
Thanks, thank you. No, thanks. Feel free. I cannot see any question.
Yeah, okay, good. One question.
We have one question from Professor Hadjimitsis. What is the impact of the atmospheric correction in percentage during the classification process?
Do you mean the general impact of atmospheric conditions or impact due to the gap filling? This is a question to question, sorry.
Yes. You can turn on your microphone, I think, Professor Hadjimitsis.
Say again, thank you, Elena, for your excellent presentation. I put the question in the chat. Say again, what is my question? When you are dealing with the satellite images and you have to apply a specific atmospheric correction, do you have any idea what is the impact? Or do you apply any specific atmospheric correction, or you using the standard automatic atmospheric correction that are embedded in Snap, for example, or any other specific softwares? Or did you face any difficulties when you apply the existing softwares for classification using the embedded atmospheric correction algorithms? Because in the literature, it is well mentioned that the impact of atmospheric correction is huge, especially if you avoid to apply the atmospheric correction. And the more well-established atmospheric correction, based on my knowledge, is the darkened pixel atmospheric correction. Did you face these difficulties or not?
Personally, to be sincere, I didn't process the data. This was done by my colleagues, but as far as I know, they use the SNAP approach.
Okay.
And as far as the percentage of the improvement of the data quality or the result quality, I'm not aware of. I didn't ask them.
Okay, another question. Did you use during the validation process in situ any specific spectroradiometers to support your results on the classified images or not?
We do not use our on-site data.
No,
Haven't been in situ. All the data which we used were taken from all three sources. So from CORINE.
There is no obligation in your project you mentioned to make any validation. No. Okay.
Like that. No, there is no in situ plan to be done.
Thank you very much, Lena. And thank you for supporting also the EXCELSIOR and our center, as my colleague Fedor Kyriakidis mentioned, because you help us a lot during the preparation of the phase 1 and phase 2 proposal, and you are helping a lot also in the implementation of the project as a member of our advisory board. Thank you very much.
Thank you for appreciation. I must thank you for inviting me to be your colleague, and I must appreciate very much the energy and invention you implemented into your project. And the result is that you received that. So this is my congratulations. It's your work, not mine. I could only support.
Thank you.
We have another question.
Yes.
Thanks for your speech again. So I suppose there is no correspondence among all these classification systems, meaning you cannot have a minimal set of classes in common that can be aligned. Is this correct?
We are going to select one, and this is adaptation based on OpenStreetMap, but we are still in the phase combining the OpenStreetMap again with other systems. So we made the conversion between OpenStreetMap and CORINE, CORINE and LUCAS, and LUCAS with the others. So the final nomenclature will be composed and will reflect the conversion. So somebody can choose this nomenclature and will get the information what these classes are represented or how these classes are represented in other systems. But for the basic part of the classification, we will use our system. And the conversion will show which class in our system reflects the class in OpenStreetMap, in LUCAS, in CORINE. This is it.
Let's wait for another 2-3 minutes if there are any further questions. Otherwise,
I have one, but I'm too, I don't want to write it down. I just verbally. So you currently have also probabilistic estimates of the classification, as you said.
Yes.
If one were to try to propagate, the uncertainty that is lying in a lot of decisions and tasks and gut feeling, and do you have any idea what would be the variability of this classification? I mean, at some point, is there any sense of, I guess you're doing that in the sensitivity analysis
yes.
down the road. Okay. But do you have any idea of, what would be the most significant impact to adding uncertainty on top of what you are dealing now?
You never know, you never process the classification for 100% accuracy. Okay. This is clear. So this should show the users where they can rely on the data to a certain percentage. This is just an information. Can I rely for 100%, for 80%, for 3%? So if it is a high probability, you can see in a significant way, I would say, rely on the data. When the probability is low, the case can be that the class itself is just, if it is 50% of grass, 50% of artificial impervious surface, and the class is determined like the grass. So the probability of the grass is not 100%, but only 50%.
No, I understand. I'm asking mostly about the, if one was to include uncertainties in all the steps of the processing, because there are, decisions that are being made, from the filtering, from the gap filling, from even the classes themselves, how they match. So an area that has 50% probability of land cover of let's say rangeland or whatever class, do you have any idea of how much that uncertainty would increase? That's the question. Because right now is the uncertainty in the classification itself, given that you have the correct training data and given that you have all, it's just the algorithm uncertainty output.
That's true. And this is what we are doing. We are improving the nomenclature, and we are still working with covariates to enlarging the feature space. So this is what we are working on.
Thank you for the presentation also. I'd like to thank you, and it's been a pleasure to listen to you. Any other questions?
We have another question in the chat. How would of this land cover product to be used in the tropical region because of the presence of cloud most of the time?
This is a similar problem like in Europe, so gap filling, but it's a question if the open data will be enough. So maybe in these cases, it would be necessary to use also commercial data to fill in the gaps, to have a wider range of what we can choose for the input, remote sensing input data. It could happen.
Thank you. Are there any?
Or maybe another case, if there is no possibility to have all the areas covered, then radar data, to add radar data for the classification, which is another step.
Any other questions?
I'm just gonna echo the often does this chat here that if there are no other questions, just for the people, thank you for everybody that's been here, and please follow our posts and Facebook pages, and in general there are things happening all along, and there are some positions for PhD students, and also we have positions that we'll be announcing pretty soon for researchers at the postdoctoral level and beyond. And again, from my side, thank you very much to Lena and everybody else that was here for this event.
Thank you for inviting me. Have a good day.
Thank you from my side as well, also to Professor Halounova and all the participants who joined today. Just to inform you that we will be sending the recorded video later on, maybe today or tomorrow, which will be uploaded in our YouTube channel. And we will be informing you for the upcoming activities and invited talks via email. Thank you all and enjoy your day.
Thank you.